You think you know what an atom is. Everyone does. Tiny thing. Little balls stuck together. The smallest piece of matter you can still call matter. You learned it in school. You saw the diagrams. Nucleus in the center. Electrons orbiting like planets. That picture feels so natural that it's hard to imagine anything else. But that picture is wrong. Not slightly wrong. Fundamentally wrong. And once you see why, you can't go back. Richard Feynman warned people about this over and over. Not dramatically. Not with slogans. He just kept saying, calmly and precisely, that the atom is not what your intuition wants it to be. And if you insist on forcing intuition onto it, you will misunderstand almost everything that follows. Start with the basic assumption. Matter is made atoms. Atoms are made of parts. Those parts are little objects with positions, moving around in space. That seems reasonable. It's how everything else works. Chairs are made of pieces. Machines are made of parts. Why not atoms? Because the atom does not behave like a small machine. Take the nucleus. Protons and neutrons packed into a tiny region. That part at least sounds solid. Then there are electrons. You're told they orbit the nucleus like planets around the sun. Already that should make you uneasy. Orbits require forces and motion. Motion requires acceleration. Accelerating charges radiate energy. And radiating energy means losing energy. So if electrons really orbited like planets, they would spiral inward and crash into the nucleus almost instantly. But atoms don't collapse. Matter exists. The universe didn't disintegrate a fraction of a second after it formed. So something in that picture is deeply wrong. Early physicists tried to patch it. They said electrons could only orbit at certain allowed distances. That worked mathematically, but it explained nothing. It was a rule without a reason, a desperate compromise. Quantum mechanics didn't patch the picture. It destroyed it. Here's the disturbing part. Electrons are not objects with definite positions, moving along paths. They don't have trajectories, they don't go around the nucleus, they don't go anywhere in the way you think movement works. An electron in an atom is described by a wave function. People often say this means it's a wave. That's also misleading. The wave function is not a physical wave sloshing around in space. It's a mathematical object that tells you the probability of finding the electron in a particular place if you look. Not where it is, where it could be found. That distinction matters more than you're comfortable with. Before you measure it, the electron does not have a position. Not an unknown position. No position at all. Asking where it is before measurement is like asking what letter a book is displaying before you open it to a page. The question assumes something that isn't there. Feynman emphasized this relentlessly. Nature does not behave the way common sense expects. If you try to imagine what the electron is really doing, you will get stuck. The math works. The predictions are perfect. The picture in your head is the problem. Now think about the size of an atom. Most of it is empty space. That phrase gets repeated so often that people stop hearing it. Empty space sounds like nothing. But the emptiness inside an atom is not passive. It's structured, governed, constrained. The electron cloud is not a fuzzy smear of matter. It's a pattern of allowed probabilities. Certain regions are forbidden. Certain energies are impossible. The atom is less like a tiny solar system and more like a standing wave, a resonance, a stable pattern that exists because anything else is not allowed. This is where Feynman's most disturbing insight comes in. The atom is not made of stuff in the way you think stuff is made. It's made of rules. The stability of matter does not come from solid pieces holding each other in place. It comes from constraints, from the fact that the universe forbids most configurations and allows only a few. Consider the Pauli exclusion principle. It says no two electrons can occupy the same quantum state. This is not a force. Nothing pushes anything away. There is no mechanism you can visualize. It's simply not permitted. And yet this rule is responsible for the solidity of matter. It's why atoms have size. It's why chemistry works. It's why you don't fall through the floor. When you press your hand against a table, you imagine atoms touching. They never touch. The electrons in your hand and the electrons in the table are prevented from occupying the same states. The universe refuses to allow overlap. That refusal feels like resistance. That feeling is what you call solid. But solidity is not a property of atoms. It's a consequence of forbidden configurations. That should bother you, because it means matter is not held together by contact. It's held together by rules about information, about distinguishability, about identity. Now ask a question most people never ask. What is an electron? Not what does it do, not how does it behave. What is it? It has mass. It has charge. It has spin. But those are not things you can picture. Spin is not rotation. Charge is not a substance. Mass is not a little weight inside it. These are numbers. Labels. Properties that tell you how it interacts. Feynman pointed out that when you strip away the metaphors, you're left with something unsettling. An electron is defined entirely by how it behaves in equations. There is no underlying picture of what it is made of. The atom, then, is not a miniature object built from smaller objects. It is a system of interactions, a set of relationships that remain stable over time. This becomes even clearer when you look at atoms interacting. Chemical bonds are not tiny hooks or glue, they are shared quantum states. Electrons belonging to more than one nucleus at the same time. Think about that. An electron in a molecule does not belong to one atom or another. It belongs to the molecule. The atom itself loses its identity. So what is an atom really? A temporary pattern. A region where certain probabilities are high and others are zero. A convenient approximation. Feynman warned that atoms are not the final answer. They are not the bedrock. They are an emergent description that works at a certain scale. Below that scale, the language breaks. Even the nucleus, which feels solid, dissolves under closer inspection. Protons and neutrons are made of quarks. Quarks are not particles in the classical sense either. They cannot exist alone. They are permanently confined. You never see a single quark. You only see combinations. And what holds them together? Not a force like a rope pulling them in. A field. A set of rules described by quantum chromodynamics. Again, behavior without picture. At every level, the same pattern appears. You expect objects. You get relationships. You expect substance. You get structure. The disturbing part is not that atoms are weird. It's that the idea of thingness breaks down entirely. Feynman once said that trying to understand quantum mechanics by visualizing it is like trying to understand music by watching the sheet music dance. The representation is not the thing. The math is the thing. Now return to the original picture you learned. Little balls. Tiny solar systems. That picture persists because it's useful. It lets engineers calculate. It lets chemists think. It lets students pass exams. But it is not what exists. What exists is a set of rules that permit certain stable patterns. Atoms are those patterns. Molecules are more complex ones. Solids, liquids, gases are large-scale consequences. This reframes everything. The atom is not the smallest piece of matter. It's the smallest stable pattern that persists under ordinary conditions. And stability is not guaranteed. Change the rules slightly, and atoms wouldn't exist at all. If the electron mass were different, if the charge were different, if the exclusion principle didn't exist, matter as you know it would vanish. That should make you uneasy. The world feels solid, inevitable, reliable. But it's balanced on an intricate web of constraints that didn't have to be this way. Feynman insisted that the beauty of physics is not in comforting explanations, but in accurate ones. The atom is beautiful not because it's simple, but because it works in spite of being conceptually alien. We accept atoms because they behave predictably, but their predictability does not come from familiarity. It comes from mathematical necessity. And here is the final twist. The atom does not exist in the way a chair exists. You can't point to it without disturbing it. You can't isolate it completely. You can't say where it is with certainty. Its properties are conditional. The atom exists as a process, a continuous negotiation between probabilities and constraints, a balance maintained by the structure of the universe itself. So when Feynman said the atom isn't what you think it is, he wasn't being provocative. He was stating a warning. If you try to understand reality by forcing it into everyday categories, you will misunderstand it at the deepest level. Atoms are not tiny things. They are answers to equations. They are allowed solutions. They are the universe doing the only thing it can do given the rules it has. Once you accept that, the world becomes stranger, but also clearer. You stop asking what things are made of and start asking why certain patterns are stable. You stop demanding pictures and start trusting structure. And that shift is disturbing because it means the solidity of the world, the permanence of matter, even the idea of objects is not fundamental, it's contingent. But that disturbance is the price of understanding. And Feynman would tell you it's a price worth paying.